Without a doubt, Cassini is one of the greatest scientific achievements in human history. This is a spacecraft that spent 13 years orbiting Saturn, longer than any probe has ever remained at another planet. A machine the size of a school bus, carrying 12 scientific instruments, traveling at 70,000 kilometers per hour through one of the most hostile environments in the solar system. And what it discovered there did not just surprise scientists. It broke them. Not one assumption, not two. Nearly everything we thought we understood about Saturn, its rings, its interior, and even the way planets form across the entire universe, turned out to be wrong. But here is the part that nobody talks about. In its very final months, Cassini did something so dangerous that NASA engineers debated for years whether to attempt it at all. It flew, deliberately and repeatedly, through a gap between Saturn and its rings that no spacecraft had ever entered. A place scientists assumed was either deadly or empty. It was neither. What Cassini found in that gap, and what its data revealed about what lies deep beneath Saturn's clouds, sent shockwaves through planetary science that are still being felt today. And one of those discoveries connects directly to something NASA found at Jupiter, something that forces us to rethink how every giant planet in the universe is built. I am your host, and you are watching this channel. Stay with me, because this story ends somewhere you genuinely will not expect. To understand why Cassini's discoveries hit so hard, you first need to understand what this mission actually was and how close it came to never happening at all. Cassini launched on October 15th, 1997, but it did not go straight to Saturn. It could not. The spacecraft was too heavy and the distance too vast for any rocket of that era to send it there directly. So instead, engineers plotted a path that would take Cassini on a sweeping arc across the inner solar system first. It swung past Venus twice, looped back past Earth, then past Jupiter, using each planet's gravity like a slingshot to build up speed. The journey alone took nearly 7 years and covered 3.5 billion kilometers. When Cassini finally arrived at Saturn on July 1st, 2004, it had to perform one of the most nerve-wracking maneuvers in the history of space exploration. To enter orbit, it had to fire its main engine for 96 minutes while flying directly through Saturn's ring plane, threading a gap between two of the outer rings at over 70,000 kilometers per hour. If the engine failed, or if a particle the size of a grain of rice struck a critical component, the mission was over. There would be no second chance. The engine did not fail. And what Cassini found once it settled into orbit immediately told scientists that everything they thought they knew about Saturn was far more complicated than anyone had imagined. Here is the thing about Saturn that most people do not appreciate. Before Cassini, nearly everything we knew about this planet came from brief flybys. Voyager 1 and Voyager 2 passed Saturn in 1980 and 1981, spending only a few days in the system before continuing outward. Pioneer 11 had done the same in 1979. These missions gave us tantalizing glimpses, but they raised more questions than they answered. The biggest question, the one that had haunted planetary scientists for over a century, was deceptively simple. Where did the rings come from? You might think we would know the answer to that by now. Saturn's rings are the most iconic feature of any object in our solar system. They have been observed through telescopes since Galileo first noticed something strange about Saturn's shape in 1610. And yet, 400 years later, as Cassini arrived, scientists were still split into two completely opposing camps, and neither side could prove the other wrong. One group believed the rings were ancient, formed at the same time as Saturn itself, roughly 4.5 billion years ago. Primordial leftovers from the original cloud of gas and dust that built the planet, preserved in deep freeze ever since. The other group believed the rings were geologically young, perhaps only a few 100 million years old, born when a moon or comet wandered too close to Saturn and was torn apart by the planet's tidal forces. Both theories had evidence. Both had serious supporters. And for decades the debate went nowhere, because no one had the data needed to settle it. Cassini was going to change that, but not in the way anyone expected. So here were the two camps, ancient rings or young rings, 4.5 billion years old or a few hundred million. And for decades, neither side could land a decisive blow. Cassini settled the debate, but not by proving one side right. It proved both sides wrong. Here is what happened. During its final orbits, the grand finale dives that we will come back to in a moment, Cassini flew closer to Saturn than any spacecraft ever had. And while it was there, threading that narrow gap between the planet and the inner edge of the rings, its instruments detected something that changed the entire conversation overnight. Material was falling from the rings into Saturn's atmosphere, not slowly, not in trace amounts, in a continuous, measurable, staggering stream of particles, water ice, organic compounds, silicates, raining downward at a rate of thousands of kilograms per second. Scientists now call this ring rain. And when researchers calculated how fast the rings were losing mass at this rate, the implications were immediate and deeply uncomfortable. If the rings are shedding material this quickly, and they have been doing so at roughly this rate throughout their existence, then the total mass they would have needed at the beginning, 4.5 billion years ago, would have been impossibly large, far larger than what we observe today. The math simply does not work. Running the numbers backward, scientists concluded that the rings are probably no more than 400 million years old. Some estimates put them even younger than that, perhaps only 100 million years old. To put that in perspective, the rings of Saturn almost certainly did not exist when the first dinosaurs appeared on Earth. They formed somewhere in the middle of the age of dinosaurs, cosmically speaking, and at the rate they are currently dissolving, they will be gone long before anything resembling human civilization could evolve again. Saturn's rings are not a permanent feature of the solar system. They are a phase, a temporary and fleeting one. And we happen to exist at the precise moment in cosmic history when they are visible. In astronomical terms, that is extraordinarily lucky. But this created a new and equally difficult problem. If the rings are only a few hundred million years old, something had to create them. And the most obvious candidate is a moon or a comet that ventured too close to Saturn and was shredded by tidal forces. It is a tidy theory. It has a certain elegance to it, except there is no evidence for it. No missing moon in Saturn's orbital history that would have been large enough to produce what we see. No impact signature. No debris trail pointing to a single catastrophic event. When scientists looked at the composition of the rings, the material is almost entirely water ice, extraordinarily pure water ice, which is not what you would expect if a rocky, complex moon had been torn apart. Something does not add up. So now the situation looks like this. We know the rings are young. We know they are dissolving. We know something created them relatively recently in geological terms, and we have no clean explanation for what that something was. This is not a small gap in our knowledge. This is a fundamental hole in our understanding of how the Saturn system evolved, and by extension, how ringed planets across the universe come to look the way they do. And the ring rain discovery made everything stranger still, because the material falling from the rings is not just disappearing into Saturn and vanishing. It is interacting with the planet's upper atmosphere in ways that were completely unpredicted. Cassini's instruments detected complex organic molecules, carbon-based compounds, arriving in Saturn's atmosphere carried by the ring rain. Molecules that had no business being there according to any model we had built. This means Saturn's atmosphere is being chemically altered in real time by its own rings. The planet and the rings are not two separate systems that happen to exist near each other. They are actively connected. They are exchanging material continuously, right now, at a scale that rewrites our picture of what Saturn actually is. Think about that for a moment. Every second of every day, the equivalent weight of a large elephant in ring material is falling into Saturn's atmosphere. That has been happening for tens of millions of years. And we only discovered it because one spacecraft, in its final months of life, flew close enough to measure it. What else have we been missing? That question is what drove Cassini's team to push even further. And what they found when they looked deeper not just at the rings but at the planet itself, is where this story takes its most unexpected turn. So we had established something extraordinary. Saturn's rings are young, they are dissolving, they are chemically feeding the planet beneath them, and nobody can fully explain where they came from. That alone would have made Cassini one of the most important missions in the history of planetary science. But the discovery that truly kept scientists awake at night had nothing to do with the rings at all. It came from what lies beneath them, deep beneath them, beneath the clouds, beneath the storms, beneath the layers of hydrogen and helium that make up the bulk of the planet, from the very core of Saturn itself. And to understand why this discovery was so shocking, you first need to understand what scientists expected to find there. For decades, the dominant model of Saturn's interior looked something like this. At the very center, a dense, compact, rocky core, perhaps 10 to 20 times the mass of Earth, made up of heavy elements, iron, silicates, rock. Around that core, a thick layer of metallic hydrogen, a bizarre state of matter that only exists under pressures so extreme that hydrogen atoms are crushed until they lose their electrons and begin conducting electricity like a metal. And surrounding all of that, the vast outer layers of molecular hydrogen and helium that give Saturn its familiar appearance. Clean, layered, distinct boundaries between each zone. That was the model. That was what almost everyone believed. And then Cassini's data arrived, and the model collapsed. Here is how it happened. Saturn's rings, as magnificent as they are to look at, are also one of the most sensitive scientific instruments ever studied. They behave like the surface of a drum. When something vibrates inside Saturn, those vibrations travel outward and create waves inside the ring system. Specific, measurable, mathematically precise waves. And Cassini, during its years in orbit, captured those wave patterns in extraordinary detail. When planetary scientists analyzed those ring waves carefully, they noticed something deeply strange. The wave patterns did not match a planet with a clean, compact, well-defined core surrounded by distinct layers. The patterns were far more complex than that. They pointed to something far more diffuse, something that blended gradually into the surrounding material without any clear boundary, something that extended much farther from the center than any model had predicted. The conclusion was unavoidable, even if nobody wanted to reach it. Saturn's core is not solid. It is not compact. It has no sharp boundary separating it from the layers above. Instead, it appears to be a vast, dilute, gradually blending region that may span up to 60% of Saturn's total radius. A region where heavy elements and lighter gases mix together in a slow, partially stable gradient that defies the clean layered picture we had built over decades. Scientists now call this a fuzzy core. And if that word sounds familiar, it should. Because NASA's Juno mission, orbiting Jupiter at almost exactly the same time Cassini was completing its grand finale at Saturn, found the exact same thing. Jupiter's core is also fuzzy, also dilute, also without clear boundaries, also far larger than the old models predicted. Two completely different spacecraft, two completely different planets, two completely independent sets of instruments and measurements, two completely separate teams of scientists analyzing data thousands of kilometers apart, and the same conclusion reached independently at almost exactly the same moment in history. This is not a coincidence that science can simply note and move on from. This is a signal that the fuzzy core is not some rare peculiarity of one unusual planet. It may be a fundamental feature of how gas giants form and evolve everywhere in the universe, and that changes everything. Here is why. Our entire model of how gas giants like Saturn and Jupiter formed depends on a specific sequence of events. First, a solid rocky core accumulates in the outer solar system. Then that core grows massive enough that its gravity begins capturing hydrogen and helium gas from the surrounding nebula. The gas piles on, layer after layer, until you have a planet. No solid core to start the process, no planet. The core is not just a detail in the model, it is the foundation on which the entire theory rests. But if the cores of both Saturn and Jupiter are fuzzy, if there is no clean solid nucleus, If the boundary between the core and the surrounding gas is gradual and diffuse rather than sharp and distinct, then the standard model of planetary formation has a serious problem. Either the cores started solid and somehow dissolved over billions of years through processes we do not yet fully understand, or they were never cleanly solid to begin with, which means the model needs to be rebuilt from the ground up. Scientists are currently leaning toward the first option. The leading theory is that Saturn and Jupiter both began with solid rocky cores, but that over billions of years, a process called convective mixing gradually eroded those sharp boundaries. Imagine dropping a sugar cube into a very slowly stirring cup of water. At first, the cube is distinct, solid, clearly defined. But given enough time and enough gentle motion, it dissolves outward, blending with the water around it until there is no cube anymore, just a region of slightly higher sweetness that fades gradually into the surrounding liquid. That is roughly what may have happened to Saturn's core, and to Jupiter's core, and possibly to the cores of every gas giant that has ever formed anywhere in the universe. But here is the problem with that theory. When scientists try to model the exact mixing processes that would be needed to produce the fuzzy cores we observe, the numbers do not quite work out. The timescales are wrong. The mixing required is more vigorous than the models allow. Something is driving this process that we have not yet identified. And there is a second problem that makes the fuzzy core discovery even more difficult to resolve. Saturn's magnetic field. Saturn has a powerful magnetic field, roughly 500 times stronger than Earth's. For decades, the assumption was that this field was generated by the movement of electrically conducting metallic hydrogen in the planet's interior, a process similar to how Earth's magnetic field is generated by the movement of liquid iron in our outer core. But there is something deeply strange about Saturn's magnetic field that sets it apart from every other planet we know of. It is almost perfectly aligned with Saturn's rotational axis, almost perfectly symmetrical. And according to the laws of physics as we understand them, that should be impossible. A magnetic field that is perfectly aligned with a planet's rotation axis cannot sustain itself. It should decay. The slight misalignment we see in every other planet's magnetic field, including Earth, including Jupiter, is not a flaw. It is a necessity. It is what drives the dynamo process that keeps the field alive. So why does Saturn appear to violate this rule? The leading hypothesis is that there is a layer deep inside Saturn, below the metallic hydrogen region, that acts as a filter. A layer that allows only the perfectly aligned component of the magnetic field to pass through to the surface, hiding all the irregularities beneath it. And the fuzzy core, with its strange gradual blending of materials and densities, may be directly connected to how that filtering layer behaves. In other words, the fuzzy core is not just a curiosity about what Saturn looks like on the inside. It may be the key to understanding why Saturn's magnetic field exists at all. And if we cannot explain Saturn's magnetic field without understanding the fuzzy core, then we cannot claim to understand Saturn at all. We are looking at a planet we thought we knew, and realizing we have barely scratched the surface. Part 5 of 5, the grand finale, Cassini's death and CTA, 1630 to 1930, English. So we had a spacecraft that had already overturned our understanding of Saturn's rings, discovered that they are young and dissolving and chemically feeding the planet beneath them, revealed that Saturn's core is nothing like we imagined, and connected that discovery to what Juno was simultaneously finding at Jupiter, suggesting that everything we thought we knew about how gas giants form across the entire universe needed to be reconsidered. And then Cassini ran out of fuel. Not suddenly, not unexpectedly. The mission team had known for years that this moment was coming. Cassini carried a finite amount of propellant when it launched in 1997, and by 2017, after 13 years of orbital maneuvers, flybys, course corrections, and scientific dives, that propellant was nearly gone. A few months of controlled flight remained, maybe less, and NASA faced a decision that had no easy answer. The simplest option was to leave Cassini in orbit and let it drift. Eventually, over years or decades, its orbit would decay, and it would impact something. Saturn itself, perhaps, or one of its moons. And that was the problem. Because among Saturn's moons are some of the most scientifically significant objects in the entire solar system. Enceladus, a small icy moon, was found by Cassini itself to be actively venting water vapor and organic molecules into space from a liquid ocean beneath its frozen surface. Titan, Saturn's largest moon, has lakes and rivers and rain, except none of it is water. It is liquid methane. It has a thick nitrogen atmosphere and complex organic chemistry that bears a disturbing resemblance to what scientists believe early Earth looked like before life emerged. Both of these moons are considered among the most promising candidates for extraterrestrial life anywhere in the solar system. And an unsterilized spacecraft, carrying traces of Earth bacteria that had survived 13 years in deep space, crashing into either of them could contaminate them permanently. It could make it impossible, forever, to determine whether any life found there originated on that moon or hitched a ride from Earth on the hull of Cassini. So NASA made a different choice. They aimed Cassini directly at Saturn. On September 15, 2017, Cassini entered Saturn's atmosphere at approximately 113,000 kilometers per hour. The atmospheric drag began immediately, pushing against the spacecraft, trying to tumble it. Cassini's thrusters fired to compensate, working at maximum capacity to keep the spacecraft stable, to keep its antenna pointed at Earth, to keep the signal alive for as long as physically possible. Because even in those final minutes, Cassini was doing science. Its mass spectrometer was sampling the atmosphere it was burning up in, sending back real-time chemical data about the composition of Saturn's upper atmosphere that no instrument had ever been close enough to measure before. Data about the exact molecular makeup of a gas giant's outermost layers, information that will help scientists understand not just Saturn, but every similar planet ever discovered around other stars. The signal from Cassini reached Earth at 6:55 in the morning Pacific time, and then, 83 minutes later, it stopped. Not faded, not weakened, stopped. In the space of a single second, a spacecraft that had operated continuously for nearly 20 years, that had traveled more than 7 billion kilometers, that had fundamentally changed our understanding of the second largest planet in our solar system and everything around it, ceased to exist. The mission team at NASA's Jet Propulsion Laboratory, people who had spent decades of their lives building, launching, operating, and learning from this machine, sat in silence. And then they began to process what Cassini had left behind. Because here is the thing that most people do not realize. The Cassini mission did not end when the spacecraft died. In a very real sense, it is still going. Scientists are still publishing new research papers based on Cassini data today, years after the signal stopped. New discoveries are still being made from the archive of information that spacecraft collected across 13 years of observation. The fuzzy core discovery itself was published years after Cassini's death, extracted from data the spacecraft sent home long before anyone knew what to look for in it. Cassini answered questions we did not know we had, and it left behind questions we do not yet know how to answer. Where did the rings come from? What created them so recently in geological terms? And why does the evidence for their origin keep pointing in contradictory directions? What exactly is driving the convective mixing that is dissolving Saturn's core boundaries? Why does Saturn's magnetic field behave in a way that our physics says it should not be able to? What is happening in the liquid methane lakes of Titan right now at this very moment? And is there, somewhere beneath the frozen shell of Enceladus, in that dark and ancient ocean that Cassini first revealed to us, something that is alive? These are not small questions. These are the questions that define the next generation of planetary science. And every single one of them exists because one spacecraft, built with technology from the 1980s, launched before the internet existed in its current form, spent 13 years faithfully circling a planet 4.5 billion kilometers away and sending everything it found back home. The next mission to Saturn is already being planned. NASA's Dragonfly mission will reach Titan in the mid-20s, landing a rotorcraft on the surface of that moon to study its chemistry up close. The European Space Agency has proposals in development for a return to the Saturn system. Scientists around the world are designing the instruments that will one day answer the questions Cassini left open. Saturn is not a solved problem. It is not a familiar landmark we have finished studying. It is one of the most complex, most dynamic, most scientifically rich environments in the solar system, and we have only just begun to understand it. Cassini showed us how much we did not know. The next mission will show us how deep that ignorance actually goes. And if history is any guide, what we find will be stranger and more wonderful than anything we are currently imagining. If this kind of science is what you are here for, if you want to be the person in the room who actually understands what is happening out there, not just the headlines but the real story beneath them, then subscribe. Every video on this channel goes this deep. Every topic we cover completely. No shortcuts, no sensationalism, just the universe, explained as clearly and as honestly as we can manage. The next video is already waiting for you.